All right, so now we're going to talk about wave properties. Last time we talked about the different types of waves. So we talked about transverse and longitudinal. And that's when I just showed you guys we talked about the direction of the particles moving and the directions of the waves. So now we're going to talk about properties of waves, and we're going to talk about them for transverse and longitudinal, okay? All right, so wave properties, they depend on what type of energy is making the wave. They depend on what type of energy that is making the wave. And let me just show you, let me do a new share again. Let me just show you what your notes should look like. Give me 1 second here. I'm going to pause the share. All right, so your notes that you're looking at should look like this. Property of waves guided notes. This is what everybody has, and it's only 2 pages. Only 2 pages. Well, there's a third page, but it's blank. Or it might not be a third page. I think I took it off. All right, so here we go. So wave properties depend on what type of energy is making the wave. Okay, so. Well, some of this stuff is already written for you. Is that right? Some of this
Yes, ma'am.
Okay, yeah, some of it's already written for you, okay? So I'll just tell you, and some of this stuff you guys already knew, because remember that first day we talked about, what do you guys know about the waves? You talked about water waves and sound waves and hair waves, and then we talked about wavelength, and we're gonna talk about crest and trough, okay? So some of that stuff you guys already knew. All right, so if you're looking at this, okay, here is the wavelength. That's going to be one of the really important properties that we're going to talk about. And it is literally, I know this is hard. Ready? It is the length of the wave. It's a wavelength. Okay, so it's the length of the wave. So we literally go from matching parts of the wave. So in this case, we can go from top to top, which we're going to figure out is called the crest, or we can go from bottom to bottom. Okay. Same thing down here. Oops, sorry, down here, we're gonna go from matching parts. And it's kind of harder to see on a longitudinal wave, but I will tell you that chances are most of the time when I'll be asking about a wavelength, I'm gonna be, if I show you a visual, it'll be this type of wave right here, okay? Not this one right here, okay? Who remembers what this is called in a longitudinal wave?
Compression.
Thank you. Compression. Absolutely. It's compressed together. It's tightly packed. All right. And then the other ones are called rarefactions. Rarefactions. All right. So here we are. Here's the vocab we need to make sure we know. Wavelength. Now, this really funky upside down looking Y, okay, is called a lambda. Okay. So it looks like an upside down Y. And it's a Greek letter, and the Greek letter is called lambda. Lambda. Okay, so it's an upside down Y. You do need to know that because a lot of times when I give you the equation, I'm not going to write wavelength, like that's just so much to write. Can you see that? Okay. Okay. Here, I can turn it on. I'm just gonna write that upside down Y, okay, so that you can see it. All right, so that's a lambda, and it's a distance between one point on the wave and the exact same place. We just talked about that. And it's a wave length, okay, a wavelength. So we measured it in meters, just like we do any other distance, okay? So wavelength is measured in meters because it's a type of distance, okay? All right, so that's the first part you need to know. Then we have on a, let me clear my drawings here. On a transverse wave, same thing. We've already talked about. The wavelength is from top to top or bottom to bottom. Okay, the matching parts. Or a rarefaction to rarefaction, or a compression to a compression. Okay, so as long as they are matching parts on the same wave. Okay, so that's a wavelength. All right. All right, so this one says, which colored line shows one wavelength? One wavelength. Is it the blue, the purple, or the green? Go.
Blue.
Okay, so I heard blue, I heard purple. Anybody else? okay? So let's see. No one said green, so let's start with green just to make sure. All right, so here's a bottom, and here's a bottom. So this should go from bottom to bottom, and this is definitely past that. This part does not match with anything right here. There's nothing missing, okay? All right, and then we got blue. Here's a top where it started. And here's a top. And here's another top, okay? And then on this one, we have a bottom to a bottom. So I heard blue and purple. I would say that your correct answer is the purple, okay? But whoever said blue, what could I do to make this one wavelength? Or if anybody can tell me, what could I do to make this one wavelength? This blue one up here.
Make it top to top.
Make it top to top, exactly. So yes, or cut it almost, yeah, right, almost in half, exactly. So somebody said top to top, which would be here to here, okay? Or cut this in half, which is basically right here. So this is actually, if you look at it, this is a wavelength and a half. Or actually, no, this is 2 wavelengths. Ooh, sorry, it's been a long day. This is 2 wavelengths, good. All right, cool. So everybody understand it's going to be matching parts. Okay, so we don't want, not this one. This is actually 2 wavelengths. This is 2 wavelengths, 2 wavelengths. This one's about 1.5, a little bit longer than a half, okay? And this one down here, this is the one that is 1 wavelength. Excellent, okay? All right. Let's keep going. So now we know wavelength, all right? So this one, which one has the, I'm gonna call on somebody, let's see. How about Kaylee, Miss Kaylee, how about which one of these has the longer wavelength? Is it this one right here? Which one of these lines is longer, or this one? So wave A or wave B?
Wave B.
Excellent. Wave B is the longer wavelength, okay? So you can see these lines get pretty tight together. So the more of these squiggly lines or waves that you see, the more waves in the same amount of time, the shorter the wavelength. Excellent, okay? So wave A and wave B. So just as a reminder, let's see where we are on our notes, okay? Distance between one point on a wave, the exact same place on the next wave. Unit is meters. That's filled in for us. The larger, oops, let me erase that. The larger wavelength, okay, we should have answered that, shorter wavelength. All right, and now we're going to come up to this box right here. So let's go back. Okay. Uh-oh. I guess I lost my presentation. There we go. All right. So now on this one, we're talking about wavelength and energy. Now look, even if I had not shown you this picture, let's just pretend, let me see if I can color over this picture for a second. Okay. Let me just color over this picture. I don't even want you to see this. I just want you to watch my finger for a second, okay? All right, so let's just say we were talking about wavelengths and energy, okay? So watch when I draw this. I want you to watch. All right, here's one wavelength, okay? Here I go. You got this one. All right, so there's a pink one, all right? And then I have this one. Just based off of like visual, like looking at that, which one looks like it has more energy, like high energy, high intensity, or which one looks lazy, kind of just like, oh, whatever. Which one looks high energy? The pink one or the green one?
Green.
Yeah, the green one. So high energy. So look, the shorter the wavelength, the more energy, okay? The shorter the wavelength, the more energy. So the large, and look at the wavelength on this one, okay? So the wavelength from here to here is tiny. Let me do it in white. The wavelength from this top to this top is tiny, or from here to here, tiny. Here to here, tiny. Versus this one is way longer on this pink one, or this one. Okay, top to top. So the longer the wavelength, or the larger the wavelength, the less energy. Okay. And the shorter the wavelength, the more energy. So this is on your notes, so make sure you fill this part in. Okay. So the larger the wavelength, the less energy you have. And the shorter the wavelength you have, the more energy. And if you ever forget that, again, you can just draw 2 different ones and see how it comes out. So draw one that's like la, 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 and then draw another one that's super smaller. Ooh, that one was bad. And see which one looks like they have more energy. Okay, so that's how we can remember that. Okay. Oh, well, let me look at that after class. All right, here we go. Ready for the next slide? Don't let me forget though. All right. So now, frequency. All right, so here's the good thing. Now I'll tell you, in chemistry, it's so weird because for frequency, we use a totally different letter. But luckily, all right, when we're talking about, oh, excellent. Jalen said we can think of the energy thing like a heartbeat thingy. Like that's great. Yes, Jalen, that's an excellent example. I'm going to use that next class period. So yeah, we can look at the heartbeat. So which one has like the higher heartbeat? That's good. I like that. Let me write that down. Okay. All right. Got that in my notes. Okay. So now frequency. Okay. This is another part. All right. Frequency sounds like the word frequent. What does frequent mean? Often, like it's occurring more often. The letter we use for frequency is F. Thank goodness. Frequency starts with an F. Okay. And it's just how many waves pass a certain point. Okay. In 1 second. All right. So in other words, if we're drawing it, you can see, let's just pretend that this was if we pretended that this bottom drawing, that there was an x-axis down here. Let me do like a really thick line. If we pretended there was an x-axis down here, probably shouldn't have chose blue, not the best color. Oh yeah, it's because of this. Can you guys, oh, you might can't see that. Let me see if I can move this. Well, I'll put the, okay, it's gonna be weird, but this is time. So let's just pretend that the x-axis is here. So this would be like, let's say this is 0 and this is 1 second. So this is all the same amount of time, but you got a whole lot more of these down here at the bottom, then a whole lot more wavelengths or waves than you do those at the top. Okay, does that make sense? Yes? All right, so in other words, in 1 second, you have a lot more of the waves down here. So this has a higher frequency. You see more of them. That's all that is, okay? So higher frequency. Now, let me ask you this. Let's say I gave these letters A, B, and C. Which one of these has the higher energy? A, B, or C? Which wave?
C.
C, excellent. So now we can even think about if you have a higher frequency, you also have a higher energy. Okay, higher energy. What does that mean in terms of wavelength? So high energy equals high frequency. What does that mean for wavelength? Low or high though, or short or long? Yes. So we know that if you have a high frequency, that means you also have a high energy. What does that mean in terms of your wavelength? Does that mean your wavelength? Yes, excellent. So Lydia said it means, yes, the question is, if you have a high frequency, like this one that we circled at the bottom, and we said that high frequency means you have a higher energy because out of all of these, C had the highest energy, just looking at it, that has a higher energy. what does that mean for wavelength? Like if I look at these wavelengths right here, like from here to here, or here to here, or here to here, what happens as you get higher in frequency? What happens to your wavelength?
It gets smaller.
Yes, exactly. So a higher frequency equals a higher energy and a smaller, oops, smaller wavelength. I'm going to use my lambda, smaller wavelength. Oh, you guys can't see that, huh? Equals smaller wavelength. Cool. So that's a good thing to have in your notes to understand that relationship that, okay, as long as if I increase in frequency, I'm going to increase my energy, but my wavelength is going to do the opposite. It's going to get lower. Okay. Excellent. All right. The other thing is the unit of measure is the hertz. Okay. So this is kind of cool. Remember, I was telling you the other day that when we change our radio station or our radio frequency, okay, what we're changing is how many waves are passing per point, okay? So we're changing, like if you ever notice, it'll say like, when you're changing your stations, it'll say like 91.9, and that's like the hertz, okay? And realistically, you don't have to write this down, but all hertz is just a fancy word for saying waves per second. That's all hertz means. It means waves per second. That's what it means, okay? Yes, ma'am. If on a quiz, you won't see waves per second, you'll see hertz. But hertz just means waves per second, okay? All right, here we go. They just give it the word hertz, okay? And then we got like megahertz, which just means a whole bunch of them. All right, here we go. I think we're almost through. Frequency, a higher frequency, the more energy. So you already said that. So if you have 10 waves, so remember I told you it's waves per second. So look, if you have 10 waves that go past a certain point in 1 second, then it's 10 hertz. If you have 1,000 waves that go past in a second, so 1,000 hertz. Same thing, 1 million hertz, and so on. Okay, so that is what we're changing when we're changing our radio stations here. Okay, the frequency. All right, so this is important to remember, but I think you guys already got that. The higher the frequency, the more the energy. And we already said the shorter the wavelength. Okay, we also said that, the shorter the wavelength, okay? Higher frequency, higher energy, shorter wavelength, okay? All right. So now, let's see. Oh, let's see if we can get to this. Oh, I know what this is. I'm gonna play this for you guys in a little bit. It is a human audio spectrum. So it's kind of cool. It's gonna talk about frequency and pitch, I believe, okay? So we're gonna talk about that in just a second. All right, frequency and sound waves. The higher the frequency, the higher the pitch. Let me see if I can pull that up. I'll see if I can pull it up in just a second. But so here you can see the frequency is not a lot passing, the pitch is very low. And when we say pitch, we mean like, for example, let me use my singing voice here. Maybe I shouldn't sing. Maybe I'll just talk. Excuse you, Lamar. Lamar's like, please don't sing. Okay. So a low pitch would be down here. So this would be a very low frequency. Wow. As I get higher and higher in my voice, this would be a high pitch. Lydia, why are you looking away from me? I don't understand why she's looking away from me. She looks embarrassed. That would be a high pitch. Which means
That was you, Miss P?
oh, did I sound good? Wait, first, before I say if it was me, did it sound good?
Yes, Tom. Yeah.
Okay, well then, yeah, that was me. That was me.
And Miss Peyton, I'm gonna be so honest with you. That did not sound good. That
Man,
was so funny.
I'm trying to tell y'all, I was almost gonna do American Idol. I'm telling you, I was almost, But I said, you know what? Let me not, because
Yes, Miss Peyton, you should do it.
American Idol.
Yes.
Wait, could you do it one more time in that voice?
Let me hold on. Let me give me something to sing. What else should I sing? Let me see. I'll just sing. I'll just give you guys just a little taste, okay? Mary had a
Look at Lydia. I can see her in the corner scratching her head.
See? I didn't want to do it because then y'all be like, oh my God, why is she teaching physics when she could be out here on the radio? Okay.
Yes, Miss Peyton.
Yes, and then I can't go low too, so I can hear.
It's fine. Me and Lydia will teach.
Little star. Yeah. No.
That was good.
That was amazing.
Thank you, but thank you. Thank you.
No problem.
Nobody appreciates my talent here. I'm just saying. I'm just trying to get y'all to understand.
That was good, Miss Peyton.
Thank you, Kaylee. I just, but I was like, I can go out here and sing and make all this money, or I could be here with y'all. So that lets y'all know I really.
Nah, go out and sing, make some money.
I'm just saying, I do a little something on the side, just a little bit. Okay. So yes, that is. I'm gonna play a cool video for you guys. So like, you guys ever heard of like dog whistles? So dog whistles, okay, they're at a super high pitch, and the pitch is so high that we can't hear it, but dogs can. And then they have some that are like super, super, super low that we can't hear. So I'm gonna play a video in a little bit. I want you guys to tell me, like, because after a certain point, I'm like, I can't hear it anymore, even though it's still going. So I'll play that in a little bit. All right, here we go. Amplitude. Again, another easy one, hopefully, or thankfully, it's amplitude. The letter for it is A. Sometimes it'll be like, oh, it's this, and the letter will be something totally different. Okay, amplitude is just how high it is. Now, not to be confused with altitude, okay? Altitude, but it is kind of similar in that they both are how high something is, okay? So it is, we say displacement of the particle, but it just means if, for example, if you have a line and that's your origin, it's just how high it goes over the line versus like here, okay? So amplitude. So let's look at it for a transverse wave. All right, so this is the amplitude. That's what I was telling you about. So like on this one, we got a pretty nice size. Oh, here we go. Pretty nice size amplitude. But then this one over here is a itty bitty amplitude. Itty bitty. And then this one's way bigger. So this is amplitude. It's just how high it is off of this line. We consider this line right here. It's called an origin. You don't have to know that, but it's like your starting point. Okay. So we call it an origin. That's what this line right here is. That's your origin. Okay. And we can do the amplitude the other way. I like doing it from the bottom to the top, but you can do it this way as well. Okay. So that's amplitude. It is also measured in meters. Also measured in meters. Okay. All right. Let's see. Wait, was somebody okay? All right, I was making sure nobody was like in the chat talking about how great I sounded. You guys let me know if y'all want me to record something for you. I mean, y'all can just make me your ringtone or whatever. I mean, that's cool. I could do that for you guys. Only for you guys though, because I like y'all. I'm just saying. Not everybody jump at once. Okay. All right, here we go. Let's see. All right, amplitude for a longitudinal wave. We probably won't do this one as much. It's kind of weird, but it's the space. It's basically like how close together the particles are. So like the little space in between, the closer they are, like right here. Oh, wrong thing. Let me get my drawing here. Like here. In between the particles. I'm not really concerned with you guys knowing amplitude for this one. Just know it for a transverse wave, okay? Just for a transverse wave. I think that'll be good enough. All right. Here we go. Clear. All right, we've already talked about this. amplitude. So we're gonna do another unit on sound, okay? Which I told you is like my favorite. But amplitude is basically how we talk about volume, okay? Volume. So if that amplitude is really small, like it is over here, then it's pretty quiet, okay? Or if it's much bigger, then it's much louder, okay? So, you know, some people in this class have a very high amplitude when they speak. Some people have a much lower amplitude. I'm not gonna call any names, I'm just saying some people's amplitude is higher than others. Nothing wrong with that. No judgment. No judgment. No, so pitch, because I can have a very low pitch and I can have a very low pitch and be louder. So a little bit different. So think, have you heard of people who have like a whistle register, like Mariah Carey? She sings in that really, really high register. She can go to a really high pitch. But just because she's singing high doesn't mean she's singing loud, right? She can be like, hold on, let me do my Mariah Carey. Like, see, she basically, who is laughing at, first of all, Mariah Carey learned that from me, okay? I taught her that.
No.
I'm just saying, I taught her what she knows, the old Mariah, you know. So, you know, she, because if you can't see me, I got my hand over my ear, so you just hit the, like that. But then I can do it loud and just be like, "Ah!" like that, you know, and that's basically what people are really laughing at me. I do not understand right now what is going on.
I was gonna ask, have you ever heard of Minnie Riperton?
Yes, I know exactly. So
Oh, she's so beautiful.
yes, so she has a whistle register. Mariah Carey, Ariana Grande has a whistle register. When she hits those really high notes, that will make my
Who is
throat
Miss
probably.
P?
Say again?
Who-
Yes.
Who is Ariana Grande?
Oh, who is Ariana Grande? She is greatness, which is hard for me to say because usually, you know, I like the older musicians, but she's pretty good. She's the one with the, what song does she sing? What's the song she sings? from?
Iggy Azalea. Right?
POV. I don't know how that goes. This,
Don't have her singing that. She go
I'll-
home and look it up. She gonna have a fit.
oh my goodness. Oh, okay. Don't. Am I gonna? Is that a bad song? Don't tell me. Don't tell me. Don't tell me. Okay.
Yes.
I have no idea. I probably have heard it before, but don't know the name of it. It's POV. There are also some guys that have whistle registers. Oh, maybe The Weeknd. He might have that. Actually, they actually had something on the radio one day about who has the best whistle register. Robin Thicke sings in a falsetto. So he sings pretty high pitched, but not a whistle register, but a falsetto. I don't know everything about singing. You know, I just happen to be naturally talented in it, but that's about it. So, but to answer Lydia's original question, pitch is how low or high, okay? But that doesn't mean that you have to be loud or, you know, soft. I know you guys are impressed right now. I can feel it. I can see it. I can feel it. I'm loving the love. I'm just saying, I love it because, you know. What?
I think you reached somebody. I think it was Simon Cowell.
So, okay, Lydia's trying to tell me that Simon Cowell would not agree with my talent, but I don't agree with that. I think he would love me.
He's he's lucky horrible. I'm not gonna bash him though.
Yeah, we're just
I'm
gonna.
about my business.
Okay.
He's like the Gordon Ramsay.
I love Gordon Ramsay. I love Gordon Ramsay. He's my friend. He just,
Oh, just watch X Factor. Like if you watch like some of the worst X Factors, they do have voice to register. They just don't have like the tone for it, if that makes sense.
exactly. That's true. I believe you. Yeah, you're right. I'm gonna I will have a concert. Let me finish. We're almost done with these notes, and then I'll give you guys a full concert. And it's gonna be great. It's gonna be great. Lydia's almost in tears. She's so excited. It's so great. Okay. All right, wave speed. So here's our one calculation for this unit. Okay, one calculation for this unit. Depends on the medium in which it's traveling. So remember medium is just a fancy word for matter. So remember we talked about it could be a solid, a liquid, or a gas. It could be air. So matter, medium, matter. Okay, so remember, who remembers? All right, I got a good question for you guys. Who remembers there was mechanical waves and there was electromagnetic waves? Electromagnetic. Which one of those needed a medium? I gave you my I gave you my shortcut. Anybody remember? I didn't hear what you guys said. What'd you say?
Electro.
Close, not right, but close. Guess again.
Mechanical.
Yes, excellent. I knew you knew the answer. It is mechanical. And somebody, Dela said mechanical too. Anybody remember how I said that we knew mechanical needed matter? Come on, it's one of your favorite.
M&Ms.
Yes.
Eminem.
Yes, Eminem. Mechanicals need matter. Mechanical needs matter. Okay. So those need matter. Velocity, we've already talked about that before. This is a wave speed. So speed is going to be meters per second. Remember, we kind of use speed and velocity interchangeably. So here's how we get how fast the wave is moving. Okay. We think about how long is the wave? Let me clear some of this off. Good grief. I got stuff everywhere. Okay. So if we want to know wave speed, we just think about, which is V, because we're really saying that that's velocity. Okay. So that's why wave speed is V, because it's just velocity. Velocity and speed are the same thing, basically. Okay. We just have to think about how frequently it passes. That's your F. Okay. And how long, I need another color. Here we go. How long is the wave? That's lambda. This lambda looks super weird. Remember, it's just the upside down Y. Okay. So that's going to be our only calculation for this unit. I'm almost positive. Yes. Okay. So make sure, and I'm going to give you guys some practice where you can make sure you know this equation. Okay. So yeah. All right. So that's wave speed. Almost done. Let's see. All right. So here's a problem. Says it's a wave has a wavelength of 2 meters. Okay. A wavelength of 2 meters and a frequency of 500 hertz. What is the speed? Well, oops, what just happened? All right. So speed, which is V, is equal to frequency, which is F. That's a blue, so that's not going to work. F. And then times wave length, which is this one. So this one's pretty easy, hopefully. We're looking for speed. So we're just going to multiply. Oops, let me fix this. I'm using my finger on my screen, guys. So I'm trying to. Here's frequency, 500. So that would go right here. And then your wavelength is 2. So that would just go right here. So it would just be 2 times 500. That's all we would have to do.
1,000, right?
That is correct. I'm going to sing an extra song for you, Jalen, because you got it right. I know, he's so excited. Oh, I really got it right too. 2 songs. That's 2 songs I'm going to sing. You guys are so lucky. Oh my gosh, I'm so excited. 1,000 is correct. 1,000, who knows the unit for this? This is speed.
Meters per second.
Yes. Jalen must really want to hear me sing. That's what that is. I can tell. He's so excited. He's going to make me his ringtone. 1,000 meters per second. He's going to old school it and be like, you're going to call his phone. It's going to be like, I'm going to be like, hi, you've reached Jalen. And he's going to be all excited. Everybody's going to be like calling him just to leave messages so they can hear me. All right, here we go. Almost done. We're going to talk about one more thing. Period, the period, not with a T, okay, period, no T. Period of a wave is the amount of time it takes one wavelength to pass a stationary point. It's kind of similar to, kind of relates to the frequency, okay? The time needed to complete one vibration is measured in seconds. So period is like the time it takes for it to pass a point, okay? The time it takes to pass a point, okay? So this is what you should be filling in on your notes right here, stationary point. Stationary means what? Stationary means not, oop, you're correct, not moving, okay? Not moving, that's what stationary means, okay? And it is measured again in seconds, okay? So your period is measured in seconds. We probably would not do any period calculations, but you can see it's just 1 over the frequency, which is 1 over hertz, or wavelength divided by velocity. Okay, we probably won't do any calculations with these though. All right, so let me just see where we are on our notes for a second. We've already passed, look at all this work we've done. Blah, 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 plug and chug, we did all that. Oh my gosh, are we at the end? It must be time for me to almost sing. All right, let's see. Waves, there's just you two. All right, so let me show you, I'm gonna stop sharing for just a second. Let me show you that pitch amplitude thing. Okay, I'm gonna stop sharing just for a second. And then we're gonna be done. What time is it? Oh, perfect. All right, so let me just show you amplitude. Oh, frequency and pitch. Frequency and pitch. Where's the one? Oh, I know it's in my, it is in my YouTube. Almost there, almost there. Library. Guys, how do I get to my, oh. How do I get to my playlist? You guys know how to get to that on YouTube? Somebody help me. Let me pause the recording. Wait, what happened to my recording? Am I not recording? If I didn't stop recording, I'm gonna be something. Oh, stop recording. Pause recording. Let me play. So this is a wave. Okay, you can see the hertz increasing. And I have it turned all the way up, but right now you can't hear anything because the pitch is so low. Our ears don't pick it up. Okay, but after a while, like I'm close to my computer and I'm starting to hear it, but I have to like really lean in.
Are you sure? Yeah, no, you don't. You don't have it turned on.
It's up now. It's coming. Can you guys start to hear it online? Can you guys hear it?
No.
A little bit? How
Now I
about now?
hear it. Now I hear it.
So you see how the frequency is increasing? And as the frequency increases, you can see the waves getting smaller and smaller. Sounds just like my singing. Beautiful. No? Oh my goodness. I'm gonna turn it down just a little bit. Look how tight, look how little those waves are now, or how many waves you have. So I can still hear it. I can still hear it. I can still hear it. Barely though. Can you guys still hear it?
Yes.
All right, I'm gonna tell you when I can't hear it. I can't hear it anymore. Can you guys hear it? So it's still a sound, but I can't hear it anymore. So that is the pitch. So I'm gonna stop the recording, but who would like a song? No? Anybody want a song?